So is this place in building 20?
Yes.
Okay. Do you have pizza?
Not yet, but I do have an announcement coming for that.
Exciting.
We're going to try something a little different this year. Okay. So I think we've got everybody. Recording is
people.
Yep, and recording is started.
Here,
so
7 online. That's pretty good.
Yeah, no, not too bad, especially for January kicking it off. So I'd like to welcome everyone to the January 2024 Northwest C++ Users Group meeting. A couple of announcements to start off. First one is I've got speakers up until June-ish, but I am looking for speakers. So if anybody would like to do a presentation, now is a great time to let me know about it. Just reach out to, I'll have my email on the presentation, so just reach out to me there and I'll get you signed up to do a presentation. Second announcement is we are going to be dropping the meetup group. Last year, JFrog was sponsoring that for us. We haven't really been getting much traffic on it, so if anybody sees anything, if you're on that and you see anything coming from meetup saying, hey, the group's dissolving, or something like that, it's just the meetup. The Northwest C++ Users Group is still going to be around. So I'll be dropping some notes on that. I think January is the last month we have that set up for. And then finally, as some of the old folks who've been around the club longer have noticed, we used to do pizza. We haven't been doing that lately. What we are going to do this summer, or try to do, and I got to get it set up, is a pizza social. So we want to be a pizza and potluck social. So potluck is optional. What we're going to try to do is basically rent out one of the little covered picnic areas or group picnic areas at one of the city parks, and we'll get a pizza sponsor and we'll go down there in place of our normal meeting. We won't have a presentation. It'll just be kind of a social gathering, but it'll give us all time to chat and have some pizza and see, hang out with each other in a little more, less formal, more personal way. One more announcement. Sometime later in the year, it'll be the second half of the year, I'm also going to do a lightning round meeting. So if you got if you don't want to do a full-on presentation that's tends to be 45 minutes to an hour and 15 minutes type of thing. But if you've got something that's like a 10 or 15 or maybe even 20 minutes, depending on who or how many people sign up, we'll have a slot for that to come together. So that'll be in the later part of the year as well. So if you're looking to do that, get your lightning talk ready. And we'll probably do it before CPPCon or before kind of like the conference cycle, so people can use this as a practice forum. Okay, does anybody else have any other announcements for various conferences or other things they would like to share?
C++ now, it has the call for submissions open, and also I'm not involved with it, but CPP Online, which is hosted out of the UK, I believe their call for submissions is open for a few more days. So if people are interested in that, they can do some Google searches and find that, or reach out to me and I'll send you a pointer to that. Also, C++ now, since our call for submission is closing near the beginning of February, we have a very short window for reviews. We have a new review system, so we're going to do kind of the three-way ranking, hot or not type of thing. Which one is your favorite type of thing. And so we're going to be looking for some reviewers, and it will just basically be bang, 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 bang of which ones you like or not. You don't have to do the full write-up. But that's a very short window. It's only going to be like 2, maybe 3 weeks, so we have to do all the reviews for those, or the rankings. So, end of report.
Okay. Anybody else? Okay, with that, I'm going to go ahead and jump into the presentation. I apologize ahead of time. I'm also the presenter tonight, so you guys get to listen to even more of me. Further apology to the board members we've already been chatting for a while. So if my voice goes, I'll apologize for that ahead of time too. Let's see. Okay, can folks see that okay? Switch my camera over.
I'm not seeing it yet.
I'm seeing it very well.
There
Okay.
it
We're
is.
seeing it now.
Sweet. So the presentation tonight is what we have lost. Here. And basically, this is going to be kind of a little retrospective on some older techniques. Technology and software development has moved forward. You know, we've left some really good, simple techniques in the background. They're really not taught anymore. Many of them are still useful. I see a lot of this in groups that I work with. I tend to be, well, folks noticing my receding hairline. I tend to be one of the older folks in the groups that I work with now, and there's a lot of younger folks coming in. And there's very different methodologies to how folks approach problem solving and their coding styles and so forth. It's one of my goals if I happen to be leading a team. I tend to like to pair up a more senior developer with a more junior developer. I find that balance works really well. A lot of the techniques and so forth that I'm going to be talking about tonight have come out of those types of interactions. And yeah, so we're just going to kind of dive into them. Also, through the talk, at the end of the talk, I've reserved some time so that folks can kind of share things they've run into. So if as we go through the talk and I'm talking through some of this stuff, if you happen to, if this happens to remind you of something you've seen, kind of make a note of it, and there'll be opportunity to, we can talk about that and share it toward the end. So the first thing I've run into is link time overlays. So all of these are going to share this general format, a description, what it is, a modern day approach, how do you do it, and then I've got typically a second slide that talks about the advantages and disadvantages of the technique. So link time overlays are a linker option that allow individual functions to be replaced or mocked in an executable. This technique is somewhat related to function overlays of the very distant past when memory was really scarce. If you think back to like the old TRS-80 days and so forth, what you had was a situation where you'd load part of your program, and then somewhere through the middle of your program would actually unload part of it and load another piece of it into memory from disk, and it would do that. And it was all just, in the past, it was trying to make better use of the limited memory that you had available. Today, this is somewhat related to dynamically linked libraries, which aren't necessarily used so much for saving memory anymore, but are used for updating and partitioning your program so it can be updated and modularized. Essentially, how do you do this? There is a linker command that you can throw that says allow multiple definitions. And the -- allow multiple definition is the GCC command for this. There's one in Visual Studio as well, and pretty much every compiler has it. They're long forgotten about. And what it does is, if you have two link time objects with the same name, that's typically considered an error. When you throw this or set this option on, it's no longer an error. The first one, the last one in the link line is the one that becomes active. So that allows you to replace an individual function by name based on your build configuration. So what you want to do is identify the functions to be replaced, and then you create a duplicate function definition in a different compilation unit. And then based on the build types, you'll include one or the other of the particular objects. And then, of course, when you do that, your program can change behavior based on that object. The advantages of this, it allows for a known common code base to be modified for testing while guaranteeing the integrity of the rest of the program. We go through these and I'll tell you where all this is headed. This is very useful if your software needs to pass a formal qualification and the exact code used in production must be modified. The linkage is also static, and the program configuration is controlled and guaranteed by the build system. So where I've found this particularly useful based on those advantages is in aerospace. A lot of times when you're testing a program or testing software for aerospace, you need to guarantee that the program you're testing is going to be the one that's going to be used in flight. However, there's also a rule that your flight code cannot contain test code. So you get into this conundrum of how do you test it without altering your flight code? And what link time overlays allow you to do is set a very well-defined and controlled partition between your flight code and your test code, and you can guarantee the flight code portions are identical. Turns out to be a really, really valuable technique in that particular case. The disadvantage, the technique is not, it's obscure, and it's not obvious to many folks these days. Most people have forgotten this exists at all. Related to that, duplicate function names are not expected and misleading folks. And it kind of gets frowned upon if you do it and you don't need to absolutely do it. But once you kind of get folks over the, once you have the need for it and you can show the advantage, I found this very, very useful for certain cases. Okay, CSV and simple file formats. So the description is using only the simplest file format needed to represent the information. What folks tend to do today is use a lot of markup languages such as JSON, XML, YAML. There's a whole collection of these. And basically what you do, most of the folks in this group are fairly senior. To write out a CSV file, you just put out your data separated by commas. If size and performance is really critical, you can also drop into a binary format and use like STX or ETX tags to mark a record. The advantage, this is simple for regular data. It's easy to read and write. Printf, scanf, strtoc, and similar are all you need to pull it in. You don't need to pull in a serialization or deserialization library. The files are typically much smaller in size. We'll look at a drill down on that in a moment. It easily interops with a spreadsheet. So I use this quite frequently. I'll just stick stuff out to a CSV file, and I just open it up in a spreadsheet, and now I can see my data. I don't need to do anything fancy with it or pull it into a JSON reader or anything like that. If it's binary, they can be even smaller and faster. Disadvantage, it's not human readable, or it's not as human readable. If you have data structures that vary significantly, a lot of the simplicity goes away. So if you have any type of irregularity in your data, the CSV file quickly loses its benefit. It's not resistant to error detection at all. There's no error checking involved. And if you're going to pull that data back into some other file, you're going to use the CSV file as interop, you need to do some type of custom parsing. Folks who have done JSON, if you're going to pull it in, you can just deserialize it back into a structure, for instance. So it's not as useful in those particular cases. Okay, very much related are simple serial protocols. It's basically the same idea we just discussed, but instead of storing the information to disk or something, you're sending it over a serial link. Again, people tend to use the more complex formats such as JSON or XML, and then they embed them inside of a transmission protocol such as TCP/IP. You're going to get the most benefit here if you're using a binary protocol, especially if efficiency is important. If throughput is important, latency is important, you'll still want to go to a binary protocol. And one of the downsides is you're going to have to develop your own packet format. So you're going to want to have the following properties to get your framing correct, because you can always lose framing on a serial protocol. You want a clear start of packet or message indicator. You want a clear end of packet message or indicator. And then you'll typically want some type of error detection. So if you look at the bottom, STX is a ASCII character. It's commonly used for start of packet or start of transmission. And then I've got the data fields of 0x1, 0x2. The third character is a checksum. So that's, you add the first two characters, put them together, and then you do an ETX at the end. That's another ASCII character. When you're decoding this, what you do is, and I'm assuming a fixed frame size here. You notice I don't have a length in there. You can add that as well. But what you do is you pull the packet in and you put a template over the top of it. Make sure your STX and ETX are in the right place. Make sure your checksum matches. Now you've got a valid packet. If you do that, you're even okay to send STX and ETX as data inside the packet, because the chance that it'll misalign is fairly small. And with you can calculate the chance that you'll get an invalid packet based on basically based on the number of bits in your framing, which is the STX, ETX, and your checksum. So in this case, we've got 8. Grab a calculator real quick. We've got 24 bits of packet information. So 2 to the 24th is about 16 million. So in this particular case, there's a roughly 1 in 16 million chance you'll get a bad packet. If that's not good enough for you, you can always do double up the STX, ETX, and checksum, and then you're up in the billions or more. Okay, advantages: they can be optimized and tuned for the specific application. So in this is actually something I ran into. The example I've got here. This was it was communication between two processors inside of a to do eye tracking inside of a virtual reality headset. The original application was using JSON, and the only thing you had to do was send X and Y coordinates, and I did simplify this a bit, but from 0 to 99 inclusive. Okay, you didn't care about errors. Because if you got a bad packet, the next one was coming right behind it. In this particular application, latency was absolutely critical. When you're doing eye tracking, you've got milliseconds. Every millisecond counts, basically. Let's just simplify it that way. So you can, in just straight binary, you can do this with 2 bytes. And because of the data range, one of the tricks you can get away with, you just set the high bit on one of the bytes to indicate X. What they were doing was a JSON packet that's about 20 bytes. So essentially, being able to send it this way in a binary format was literally 10 times faster, and also 10 times less latency. And that was a make or break for this particular application. Very, very simple change to make in the code. Disadvantages: not human readable. It's not parsed by your protocol analyzers. You're going to have to write custom code on both sides, but hey, we're sending a couple bytes. It's not that big of a deal. If you have complex or variable data, though, this does become much harder to work with. Okay. Related to that is simple serial ports. I can't see folks in the room anymore, but how many people remember the old RS-232 port? And if you've done industrial, you've also run into RS-422 and 485, which are the differential versions of 232. So these are all simple 2 to 9 wire serial ports. They've been around for decades. They used to be everywhere. Now you only see them in special use cases. Last time I saw an industrial machine, they were even using USB, which really surprised me. Most applications today are using Ethernet for long distances and USB for short distances. I even see some of them starting to use Bluetooth on occasion. So very, very complex and potentially error-prone communication protocols. How do you do it? Most of the PCs you buy today do not have an RS-232 port on them, although if you build your own, the motherboards actually do. I built a new system this summer and it had one true serial port on the motherboard. So you can still get them. If you can't do that, you can get a PCI card. They're still very available. And you can always use a USB to RS-232 dongle. If you're going to go the dongle route, I recommend using the FTDI chipset. That will be listed in the specs for your USB converter. That's the most common and widely supported. I have used other chipsets in the past, and especially if you're going to go USB, USB can do some very weird things to you in the way that it basically buffers, packetizes, and ships the data from the USB to the physical port. FTDI has that pretty well under control. There's still a couple of things to watch out for in terms of splitting packets or things like that, but FTDI works everywhere and it's quite robust. If you're not using a USB port, you can also get Ethernet to RS-232 converters. Those are also available. And basically, modern Ethernet is fast enough that you don't really notice the intermediate translation of onto Ethernet, off of Ethernet, onto RS-232, back from RS-232 onto the Ethernet, back to the computer. Ethernet's fast enough compared to RS-232 to pretty well hide all of that. Yeah, I got a question. Somebody's got a hand up.
That's me. I remember back in times of Windows 95, Windows 98, the changing of COM port configuration was unstable. For example, if you have a message and you want to set a parity bit to 0 in the firstmost byte and to 1 in all the rest of the bytes, when you do that, that actual switch happens at an unpredictable moment. So more than 1 byte goes with 0 parity bit, and less than expected number of bytes was going out with parity bit set to 1. I just wanted to know, has this changed since then, or is it still that case?
I would say I haven't run into that, but I haven't switched the parity bits during operation. Usually the pattern I do is I set up the communications protocol at the start, and then I start talking. The things I run into with the FTDI or with chips other than the FTDI are kind of related, where like some of the handshake lines will do something weird and they'll glitch or something like that. I have run into that. I'd say FTDI probably has it pretty well under control. But yeah, you're describing exactly some of the type of weirdness I have seen in other systems.
Okay.
Yeah, and I didn't realize, at least when I've run into it, I didn't Well, let me drill down on that for a sec, because a couple of times when I've run into stuff, it was not necessarily the hardware, but it was the USB drivers in Windows that were doing weird things to me. I have run into that before. So changing the drivers cleaned some of that up. In all honesty, for probably the last 10 plus years, if I ever have to do this, I use FTDI, and that's been it. So I haven't had any real problems. But prior to that, I did run into some weirdness like you were talking about.
Okay.
Okay. Other questions? Yeah, and by the way, I forgot to mention, if somebody does have a question, just raise your hand. With Robin popping in like that, I actually have a nice little window on my screen now, so I can see if somebody wants to interrupt me. Which very strangely showed up, Robin, the minute you did that. Speaking of strange operating system things, or strange Microsoft things. Okay. Anyway, to do this in code, you just basically open the serial port as a file and start reading and writing to it. This is pretty similar between both Windows and Linux. You do have to configure the communication parameters, the baud rate, start bits, stop bits, parity bit, and so forth. Depending on exactly what you're doing, sometimes you can just configure that in the OS and it'll stick. Sometimes you have to make a special call in to the file system to actually set that data. Let's see. Okay, advantages, they're simple to use and you get very fine-grained control. Since something Robin was saying, I actually have used the handshake bits as bit twiddles to actually control things other than the actual serial port communication. You can set the RTS and CTS lines in one case, and the DTR, and can't remember the pair for the DTR line. But anyway, you can set those in code and use those as additional handshake lines that are kind of sideband to the actual communication. Again, I haven't actually run into the problem you were mentioning, Robin, where they come up at different times. At least when I've done it, they've always been basically in sync with the data I was sending. The simple serial ports are also extremely robust to environmental influences. You can get chipsets that are radiation hardened. And some of the stuff I've done, that turns out to be rather important. So far as I'm aware, there is not any Ethernet chip that is radiation hardened. So that's one advantage of them, is they can, if you're doing something like X-ray machines or something like that, where you are around radiation in some ways, these types of links are more robust. You can also connect to very simple microcontrollers and hardware devices. You come off the PC, don't put 12 volts into your microcontroller, put some drop-down resistors in place and some protection circuitry, but then you can go straight into a little microcontroller that's too small to even have any type of USB or Ethernet controller on it. Latency is also very well defined. So in both USB and Ethernet, when your packet goes out is actually based on network conditions. Basically, with the simple serial port, if you send a byte out, it's going out pretty much immediately. It's not completely deterministic because you got the clocking, but it's within a clock cycle or two, not within a packet cycle or two. Disadvantages. You don't get any networking stack. You're going to have to build that yourself. The baud rates are quite low by today's standards. They top out at about 1 megabit per second. But for a lot of work, that's perfectly adequate. The range is also limited by compared to today's standards. RS-230, well, RS-485, I think you can get up to 100 feet or so on that without doing some like high-end drivers or something. But you're not going to go like the 300 feet or something that you can do with Ethernet or some of the other protocols, or some of the other, not protocols, medias. And the cabling can also be heavy by today's standards. If you look at an old DB9 serial cable, it's 3 or 4 times thicker than, say, a nice little Ether or a nice little USB cable. It's about the size of Ethernet. Okay, this is one of my favorites, stream file processing. So it's interesting because this stream file processing didn't used to exist. The default was you always took information in packets and processed it as a stream because you couldn't read the entire file into memory. That kind of went away, and now it's coming back. Basically, the idea is you treat the file like a set of information packets, and you read one packet at a time and process it. What I see people doing today is reading the entire file into a large array of memory and processing that whole array. So this is actually one of my pet peeve ones, because I was working with a guy and he was having trouble. Basically, his file processing was taking too long, and these were roughly, say, a 1 to 2 gigabyte file, right? And we were walking along, and you were talking about, why he was having trouble reading this in. So I was like, so what are you doing? And he's like, well, I read the file into memory. And I was like, you do what? So essentially, that's not exactly the way to do it, especially if you've got a large file. Some files today are in the hundreds of gigabytes, and you just don't have that much memory. Basically, how do you do this? You open the file just like you would normally, and then instead of reading the entire file into memory at once, read just as much as you need for a single unit of work. So typically a file has multiple records in it, or it's time series data and it's a series of bytes. It could be tagged bytes, but typically, even in the largest files, a work unit is not more than a few hundred bytes. Maybe if you're doing something really large, like a kilobyte at a time or something like that. But basically, you keep reading the file and processing the work units until you reach the end of the file. Advantages. In most cases, the code to do this ends up being no more complex than doing it in memory. It is different, but the code to just read a packet at a time is about the same complexity as pulling it all into memory and then decoding the packet in memory, right? So you're still decoding the packet. The resulting code can also be used on any type of a stream, including a network socket. So this is something else I do pretty typically. If I want an automatic playback, right? I can store that data to a file, and now I can open the file or the network socket, and I can use basically the same code to decode that stream and process it. You also get some parallelism for free. If you're reading it in packets, the OS is going to buffer and cache the file. So when you read one packet or one work unit, the OS is grabbing the next one. When you come back and finish processing the first work unit, the OS already has the next work unit buffered for you, typically. So it actually improves your performance, and you don't have to do anything to do this, unless you specifically disable buffering in the OS or use some type of like a raw or canonical file stream, which takes special steps. You get this parallelism and performance improvement for free. You can also handle files of any size, including live streams that run forever. So you're no longer limited to the size of file you can pull into memory. Disadvantages. Random access to the data structure is harder in some cases. Depending, it could be impossible. If you're in a live data stream and you want to go back 2 hours, not happening. And some parsing operations do benefit from a state machine, and that will make the implementation harder for that type of structure or that type of file format. Okay, to a hardware tech, blinking an LED and a debug GPIO. So this is if you're working on like a microcontroller type of a project. This is most effective during board bring-up. So what you do is configure a simple GPIO line to act as an output, and you toggle it from within your code. Just simply blink the LED on and off. This used to be the de facto board bring-up test, right? When you got the board back from the people who fabricated it, and you started loading your code and stuff onto it, when you got to the point where it could blink an LED, you were over the bring up hump, right? You've got the CPU up and running, you've got the resets up and running, you got the power supply up and running, and you can blink an LED. What I see people doing today is actually, instead of trying to bring up the board using a blinking LED, they try to bring up the entire JTAG debugger and or a debug port, debug serial port on the device. Those are much more complicated interfaces. The JTAG, you typically need to get the JTAG up to even get code into the thing, but you don't necessarily have to get the entire debugging stack up and running to get code in. The debug port, you have to get the JTAG up and running. You have to get all the resets up and running. You typically have to get some type of a monitor up and running. And then you have to get the serial port up and running. And it's a lot more complicated than just bringing up a debug. And I've actually seen people send out, hello world over the debug port. Cute, but a lot more work than just blinking up or bringing the board up to just blink an LED. Basically, how do you do this? You construct an absolute minimum program or use an existing sample program. You configure a single line or port, whichever happens to be simpler. And then in your code, you just go into a tight loop and set the output high, set it low. Sometimes you may put a delay in there, but just toggle it high and low. And then you can look at that state with a scope, a logic analyzer, collect a low power LED, whatever. The idea is to just basically show some code running and verify that the code is running. The advantages. It's extremely simple to get working compared to other approaches. The timing and latency is extremely low compared to other approaches. So once you get, especially with the GPIO, I typically reserve an entire 8-bit port, if I can, on the development board for doing just the debug IOs. And even after I get the board brought up, it's very common for me to just simply hook a logic analyzer up to that port and toggle those IOs and use them basically just like you would printf statements in the code. With that, you can convey the system state in real time. You can track individual state changes. You can look at them on the scope and look at timing in very, very detailed fashion. And yeah, it's a lower level, but much, much simpler debugging technique. You can also debug issues where the processor will not stay running. I've actually run into this one on a pretty regular case where somebody it's very common to put a watchdog on the board. And basically what a watchdog is if you don't tickle it, the watchdog will reset your processor. And if all you've got is the JTAG debugger on there, all you see is the board comes up, it stays there for about a second, and then you lose your JTAG connection. And then you start over. If you've got a blinking LED going, what you will see is you'll know the code is running because you'll see the LED blinking, and then you'll see it all stop and reset. And that's usually an indication that a watchdog or some external monitors reset your processor. If you've got these GPIO lines set up, it gives you a little bit lower level interface to see that, where a JTAG just blows up. The other problem with JTAG is sometimes they're unstable. I've seen it fairly common when you're first bringing a board up, if you don't have the JTAG lines properly terminated or balanced, you can get the JTAG running for long enough to get code into the processor, or maybe even it'll stay up for a couple of minutes, and then it'll glitch and go down. If you've got the watchdog, or excuse me, if you've got GPIOs and various other simpler debugging techniques, you can use those to know whether you've got a JTAG link problem, a code problem, a watchdog problem, or some other type of monitoring problem on the system that's kicking you into a reset. Disadvantages. This always requires some type of external hardware to monitor. So you have to be familiar with like scopes and LEDs or logic analyzers or something like that. And it's always going to require some basic electronics knowledge to set up. The other disadvantage, you can only send limited information. Unlike a JTAG, you can't just dump your entire register set out to the to the blinking LED. That's not practical. But you can get very meaningful information out. Okay, bare metal coding. This is basically creating your application directly against the hardware without using a framework or an operating system. What I see people doing today is even on small ARM processors, they put Linux on it. One of my pet peeves, I've got a home automation light switch in my house. It's connected to Wi-Fi. I can, ask Alexa to turn on and off, or Google to turn on and off my lights for me. That light switch runs Linux. It's crazy overkill. It means my light switch takes 20 seconds to boot when it's a power failure. In addition to it's drawing a reasonable amount of power just sitting there. It would have been nice if they could have just used, something a little lighter than a full-blown Linux on it. Well, it's not a full-blown Linux; it's stripped down Linux, but something other than Linux to run that app. Basically, how do you do this? Create a description of what you're trying to do, requirements. If you've got a simple application or it has hard real-time requirements, consider working directly against the hardware. The exact details depend a lot on what you're trying to do, and there could be several additional, we could do additional talks on this. It's basically a trade-off. Is it going to be easier? Because keep in mind, an operating system like Linux actually creates a lot more work for you as well. If you're trying to do something in real time, you need to get real-time Linux patches in there and so forth. A lot of times it's easier to just skip the operating system and go directly to the metal. You can implement more You can implement more hard real-time applications, so tighter control. Development can be simpler and faster in some cases. You'll always use lower cost hardware because you're not paying for this RAM and power to run the operating system. Your boot times are greatly improved. It's fractions of a second and compared to several seconds in many cases. You get fine-grained access and control to all of the available hardware without having to write Linux kernel drivers. The other technique is you can use your interrupts and DMA engines to simulate a multi-threaded application, and it actually works out that you improve your determinism and latency quite a bit when you do that. Disadvantages, you may have to actually do more coding to implement, like putting in quotes, device drivers, basically depending on how complex your devices are you're trying to control. There's one intermediate step I came across on this. The STM32 line of processors has a system called MABYE now. That's actually been there for years. I just came back across it recently. It actually gives you these low-level device drivers in nice, easy-to-use packages without the overhead of an actual full-blown OS if you don't want it. So there is kind of a half step in here for certain processors. Your development debugging tools are going to be more limited. You don't get GDB. You don't have an operating system. And you're going to be doing real embedded systems development by its very nature. You don't take your embedded system and turn it into a mini desktop. You're really doing an embedded system using this technique. Okay, next one is hand-optimized functions. So this is creating a dedicated function that does only what you need to do in place of using a library function. So this one's a pretty controversial one. This one you really need to think through. The modern day approach, because we have a lot of libraries, is I need to do something. Where's the library that does this for me? The main takeaway here is you're going to trade development time for execution time, right? So if you go grab a library, that saves a lot of development time, but that library is generally a general purpose library, and it's going to do a lot more work to handle that general case if you only need to do something really simple. Maybe that's okay. Maybe that overhead is going to create a problem for you. So first thing to do, what is really special about what you need to do? If you've got something that, you know, it's a generic thing, it's not really special, go use the library. Okay? If you've got something special, profile and evaluate the available libraries and really make sure they're not going to work for you. While you're doing that profiling and evaluation, you're going to get a better understanding of why the available libraries don't work for you. That's a key that you need to know if you're going to go, you know, do it yourself. Go ask a friend or coworker, get a second, third, and fourth opinion. Okay, make sure you know really why you need to do something special before you go do it. Otherwise, you're just going to reinvent the wheel, and you're going to also reinvent all the same problems the library has already solved for you or caused for you. So if you've made it to this point, you still think there's something special about what you need to do, then code it up. The advantage, it's going to be completely tailored to exactly what you need to do. It'll be typically simpler, and you're going to save a lot of overhead. And you may come up with a better way of doing something and get some really nice kudos. Disadvantage, it's going to take a lot more time to develop, debug, and maintain. It is possible you'll spend a lot of time to develop a solution only to find out your solution is no better than the one that you could have just used in the library. And your coworkers are going to make fun of you and make you justify as to why you did it yourself. So you better have a good answer for them too. Okay, next one, simply installed programs. I'm a real fan of statically linked programs. The program consists of one file, that's the executable, and everything's in it. The modern day approach is to create a large set of files that need to be installed, and then you create an installer application or wrap up everything into a Docker container. Basically determine if a single file is really appropriate for your application. You should already have, but put a development process in place that controls the addition of dynamic linking, configuration files, registry settings, and so forth, because you have to track that. And you have to put all that into your single file. And then there's a lot of ways to embed binary data into an executable file. I list a talk here by Jason Turner, The Power of Compile Time Resources. If you get into this, go look at that talk. He shows a whole bunch of techniques for putting binary resources into a single executable file and how to get them back out easily. The other thing you can do is the first run of a single executable can set up the registry settings and any other special configuration in place of your installer. What I typically do is when I'm doing this, I'll have the executable, when it runs, it goes out and looks and says, is this registry flag set? No. Okay, now I know I need to go configure all this, and then the program just goes through and sets up my registry settings, for instance, or a database or anything else I need set up that would normally be a separate file. Advantages, the application is easily moved around. No installer is needed. You don't have any dependency issues, and you, by definition, stay away from DLL hell. Your application can actually be simpler to develop in some cases, and your application performance can be faster in some cases because it's not reaching out to pull in all these other resources. The architecture of your application is going to be limited. There's a lot of techniques you cannot use with this because, well, you're statically linked. If there's an update, the whole application needs to be replaced. I actually probably should have put that as both an advantage and a disadvantage. That can work either way for you. And not all dependencies that you need or may need to use can be packaged into an executable. There's some things that are just, insanely huge files or something. Like you're not going to package, a multi-gigabyte resource into an executable. That's just not going to work too well. Okay, and this is the last one. Has anybody seen a cardiac cardboard computer? Oh, somebody's got a hand up. I can't tell who.
Yeah.
What you got?
Going back to those simply installed programs, do you have an example of that, like particularly like consumer facing? Because I'd imagine that'd be quite difficult nowadays.
Let's see. I'm trying to think of a
I
good
know that all the
example.
sysinternals programs used to be simply installed programs like that. And they did something very interesting where they had the 64-bit program inside the 32-bit program, and it was set up to run whichever architecture you had, but it was just one exe binary.
Yep. The one that's coming to the top of my head that I just pulled down, there's a lot of utility programs do this now. Let's see. One of them is textanalysistool.net. This is actually a .NET program, so it's not quite the same thing, but it is just one file. I also pulled down a utility program for looking at my GPU and the CPU and GPU stats, and that was just a single executable. You just pulled it down, unzipped it, and ran it. So a lot of utility programs do things like that currently.
Thank you.
Big programs like Word and spreadsheets and web browsers and stuff like that, no. But video games, absolutely not. But yeah, some of the utilities, or a lot of the utilities actually work that way. So Cardiac is a cardboard computer. Has anybody seen this before? Okay, I suspect not. So this little creature is actually how I got into programming. My dad worked for Boeing. This was in the 1970s, maybe late 70s. And he was taking a class in Fortran on the mainframe computers that literally worked with punch cards, right?
Done that.
Yep. This was a teaching tool that was used at that point in time, okay? What this Cardiac is, it's a cardboard computer, and you can see the little sliders on it. And it basically, what you did is you put an opcode into the little memory cells on the right. You had a register set on the two little sliders that you see on the left hand of each half. You can see the accumulator in there with a plus sign, and then you can see the three sliders at the bottom. You decode the opcode by setting those sliders, and the opcode shows up in that little window. And then the little bars in the window show you how the data flows. Essentially what this does is simulates an arithmetic logic unit and a decoder inside of a processor.
You probably can use your mouse to point to specific parts of the picture.
Yeah, let's see. Can folks see my mouse?
Yep.
Yes.
Yeah.
Okay. So this is the program memory. This little bug, these are actual little holes, and you walk the bug down. That's your program counter. This is a output register. This is an input register, and they have values on them. This is an accumulator. You see a plus sign there, and I think that would also switch to a minus. These three sliders were used to set the opcode in this little window. So what you would do is you'd read the opcode off of the program counter, set it in the window, carry out the operation based on, you can see the sliders moving here and the plus sign would move and so forth. And then you'd step the program counter and you would manually execute every single, essentially, assembly language instruction. I really, really, really wish they had these around today. One, they're kind of fun, but two, they very unambiguously showed you how a very, very simple computer works. And once you play with this thing for 10 or 15 minutes, your intuitive understanding of what's going on in the machine, it's hands-on. It's not an abstract thing anymore. It's very hands-on. To that effect, I'm going to give James Newton. He's a member of the Seattle Robotics Society, which I'm also involved with. He actually reminded me of this when I gave this talk at the Seattle Robotics Society. And so I put it in there. He's actually gone so far as to develop a web page that does this. It's not quite as good as the hands-on, but it's the same concept, and you can get at it from https://jamesnewton.github.io.cardiac. So many thanks to him. And yeah, if you're trying to get somebody into what's happening inside the computer, this is absolutely a wonderful tool. So with that, I'm going to stop sharing screen. I wanted to save some of the rest of we've got about a half hour left while we still have the room. I wanted to just turn this over to other folks and see if anybody else has some stories, nightmares, techniques they would like to share.
Lloyd, could you go back one slide? I want to copy that URL.
Yep. Oops. Did it share? Nope. I shared the wrong screen. Hang on. Yeah. Hang on. Hang on just a sec while I get my.
Or if it's easier, you could just ping the URL to the chat.
There we go. Okay, let me share the correct screen this time. Nope, still didn't get the right screen. Okay.
There it is.
Can you guys see it okay?
Yeah.
That was cool. I think he has an insightful view.
Yep, got it. Thanks.
Okay. Okay, so open discussion. Anybody have anything they want to share? Techniques, comments? Growing tomatoes?
Yeah, I had a question about the linker page concept.
Uh-huh.
You can hear me.
Yep, I can hear you.
Yeah, I had a question about the linker page you had on the slide. So I would imagine you could do that in during assembler time, simply separating the header file and implementation file. So what's is there any particular reason why you'd want to do it in the linker, or?
Yeah, so you can do it at compiled, or you can do it with conditional compilation. But in the particular case I was looking at, it was an aerospace application, and conditional compilation is generally frowned upon in aerospace, specifically because you have a variable configuration for your flight code, and that's generally not allowed. So by doing it at link time, your source code is constant. You can guarantee that your source code won't change. And then you encapsulate the variable portion in your build configuration. And then you do have to go take the next step. to make sure your build configuration, does what's intended for flight mode and what's intended for test mode. But it pulls it out and pulls it into an area where it's easier to validate.
I'm sorry, I still don't see the difference between a special link switch and simply swapping out a different object file.
So you could do that as well. You actually could swap in a different object file, and then your build script would include a different object file. That's another way to do it.
Right, okay.
Yep, so that would
But that-
also work.
But that's not applicable to the aerospace industry, correct?
Depending on how you did it.
You said that the binary should stay the same.
Yeah, the binary should stay the same. So if you're going to swap it out as a compilation unit, I can see ways that you could get that approved. In a particular case where I did this, I did not use source files. I did it as two separate repositories. So the repository that built the flight code was standalone, right? So essentially the flight code built, right? Just like you normally would. So you did a normal production build. Then I grabbed those assets and made the test build on top of them. So when I was done, I actually had both sets of executables. And I had a hard division in the repository so that when they went to go validate the flight code, they never saw the test code. It just wasn't part of the equation. And for our particular case, that worked really well.
But either way,
but
you're putting in a different object file.
Yes, either way, you're putting in a different object file. But here's the catch: I can guarantee my test object, only shows up in my test code. I can guarantee my test code will not end up in my flight code. And that's done by very careful structuring of the file system. So yeah, it's kind of a niche application, and yeah, we can dig down into that a little more at some point if you want to, into how that works. The whole package, you have to look at how the build system and the repositories and the validation is going to be done.
Okay.
I suppose the answer to your question is it's a regulatory loophole. In some regard, yeah.
Yeah. Well, it's basically you run into this problem of your flight code. Your flight code has to be the minimal code possible, right? You're not allowed to have dead code for any reason in your flight code, right? If you're going to test something, you frequently need to look at things that you don't need to look at in flight. Those are absolute contradictions of each other. I can't look at my status in detail if I'm not going to use it in flight. And I'm absolutely not going to look at that much detail in flight. So yeah, it's kind of a loophole, but the other hand, it's a catch-22.
Could you do like a debugger solution, right? Like you do your testing through some kind of debugging interface, so you don't actually change the executable at all, right?
Yeah, in some cases you could also, I could see doing that too. But in that particular case, you're not going to be able to run real time.
Yeah.
So that's the trade you're going to make in that scenario.
So I have a question about the file.
There is no perfect solution to this. So you're always making some type of a trade-off. Yep. So next question.
So I had a question with the file thing. So what I've usually done is just to use memory mapping. Instead of reading a file, I memory map the file.
Oh, you memory map the file into memory.
And then go through it. And then the operating system is doing the loading it in page by page, right? And the size does not matter, right? You can,
That's
as long as it
right.
fits in.
As long as you got a 64-bit OS, yeah.
Yeah. Yep. Yep.
Nope, that would also work. Yeah, that's another good technique. I haven't seen that one done too often.
But I've been doing that since the 90s,
Oh, cool.
since it was added to the OS,
Put my camera back facing forward here.
Yeah, and the other thing that I'm an oddity, but I actually write all of my own code. Like you talked about, write a function here or there.
Yep.
I write all of my own, including not using the CRT. And,
Oh, wow.
And you can get very small executables if you do
Yes,
that.
you can. Yep. And yeah, it's always a trade-off.
Yep. Yeah,
Yep.
It's for sure that I spend a lot more time writing code than I could if I just pulled it out of wherever.
Yep. Okay. Other questions, comments? How are we doing for time? 8:09.
You were talking about, let's see, which of these questions was I doing? Sorry, my mind just went completely blank. I'll come back if I remember it.
Okay.
Oh, I remember. You were talking about a program that will check things like registry keys, check for the existence of databases and things like that, and initialize that stuff at the beginning, presumably only once.
Yeah.
Doesn't that end up with a lot of code that never gets used again?
Yep.
It still gets pulled up into memory.
Yeah, yep, that's the downside of that is, and it depends on how much you're going to do. If you're just doing a few things, it's not a big deal.
Right.
But yeah, you're dead on. It does end up with the executable being larger than it absolutely needs to be.
Okay, thanks.
Yep. And yeah, with all of these techniques, there's it's a trade-off. They're going to help in some cases, they're going to hurt you in other cases. One of them that really got me with the loading the file into memory. We were doing multi-gigabyte files, and what the younger folks were doing is they got to the point of, oh, I can no longer fit this in memory, so they started segmenting the files, right? So instead of one 10-gigabyte file, they would send us three-ish roughly 3-gigabyte files, right? Or three 3-gigabyte files and one 1-gigabyte file or something like that. And that just drove us nuts because on our side, we were doing the analytics on these. We had to put the files back together. Sometimes they would forget to send us one, so they'd send us 3 files and all of a sudden the middle was missing. They'd send us the files out of order. So it wasn't just a matter of pulling it in and, it wasn't just a matter of the coding aspect of it that became a problem in this case. It was the whole process by which the files were generated and handed around the team. So, okay, other questions? Okay, with that, I think we can wrap this one up. Thanks, everyone. We'll get the video and slides posted here the next day or so. And yeah. Any last comments? Peter, do you want to have them stop the recording then?
Yep, I'll have them stop the recording.
Okay. Oh, that is weird. You're like 2 seconds delayed on the video.